Welcome back, and in this video we're going to be looking at the typical reactions of benzene, and very importantly we're going to be looking at the mechanisms. And the mechanisms are some of the most important ones you're going to come across in the upper sixth, and you need to be very careful that you learn them correctly. So we're picking this up on page 10 of our notes, and the first thing we're going to do is look at the combustion. Now the experiment you did, you should notice that benzene burns with a particularly smoky flame. The reason for this is the very high carbon to hydrogen ratio. So with excess oxygen, you can burn it to form carbon dioxide and water. So the equation for this is C6H6 plus a lot of oxygen, and it's going to make 6 CO2s, and it's going to make 3 waters. So then we have to balance the oxygens, and we have 7.5 oxygens. Okay, so benzene is a liquid at room temperature and pressure. Oxygen obviously is a gas, carbon dioxide a gas, and at room temperature and pressure, water is a liquid. Now benzene is very resistant to addition reactions, so it doesn't tend to undergo them. The reason it doesn't undergo addition reactions is it would have to break up that nice delocalized ring of electrons. So rather than doing addition reactions, it tends to undergo substitution reactions. But because you've still got that delocalized ring of electrons, it reacts via electrophilic substitution, as that maintains the ring structure. So from lower sixth, we can remember what is an electrophile. An electrophile is simply a species with a vacant orbital. It can therefore accept a pair of electrons and form a dative covalent bond. Now that electrophile can be positive or it can be delta positive. Now the next bit of this is just a bit of revision, and it's just to remind you of the mechanism for the reaction of an alkene with something like hydrogen bromide. This is electrophilic addition mechanisms, remember. So we're going to take our cyclohexene with its single double bond. So this is going to react just like any normal alkene would, and we're going to take our hydrogen bromide, HBr, and we've got a delta negative delta because the bromine is more electronegative than the hydrogen, so the electrons spend more of their time up this end of the molecule, leaving this end delta negative. What that's going to do is going to draw the electrons from the bond, and please make sure you're taking them from the pi bond there to the hydrogen, and those electrons pushing in pushes out the electrons from the bond between the hydrogen and the bromine onto the bromine. And again, make sure that line starts from the bond. Do remember there's only 2 places you can pick up a pair of electrons from. One is a bond and the other is a lone pair. So this makes an intermediate. In this case, it doesn't matter where I put my extra hydrogen. We put it there, and it leaves this carbon here as positive. But I've got a bromine now, or bromide I should say, with a full negative charge and a lone pair. That lone pair is attracted in to that carbon with the positive charge, and we get our compound. I go back to a skeletal, and I've made bromo cyclohexane. Now this works very well for electron-rich double bonds. It doesn't work very well for benzene. So benzene is not going to be able to react with hydrogen bromide in this way. So instead, most of the mechanisms are electrophilic substitution mechanisms, where we're substituting the hydrogen on the benzene ring for something else. And these mechanisms always take place in 3 steps. You form the electrophile, then the pair of electrons is drawn from the ring to form a dative covalent bond with that electrophile, and then the ring is reformed, and lastly we get the regeneration of the catalyst. So the first one we're going to look at is the nitration of benzene. So the reagents for this reaction are concentrated nitric, HNO3, and concentrated sulfuric acids. Now in this case, the concentrated sulfuric acid is my catalyst and the concentrated nitric acid is my reagent. Now the conditions for this are heat under reflux at 55 or thereabouts degrees Celsius. And that temperature is actually important, and we'll come back to that later. So the formation of the electrophile, we need to make this positively charged ion. So the nitric acid is going to react with the sulfuric acid. Now in this case, the sulfuric acid is a stronger acid. You're going to study this a little bit later on when you do acids and bases. And it causes the nitric acid to gain a hydrogen ion. So it becomes H2NO3 positive, and obviously the sulfuric acid has lost hydrogen to become the ion HSO4 minus. Then very, very quickly, that H2NO3 positive loses a molecule of water to become the slightly more stable NO2 positive ion. Now, quite often we show this, instead of it in 2 steps, we show this in 1 step. So this is probably the one you want to use in the exam. So you have your sulfuric acid, H2SO4, very concentrated, and you have your concentrated nitric acid, and you're going to make your NO2 positive, and you're going to make some water, and you're going to make your HSO4 minus. And it's this that I'm interested in. That is my electrophile, my NO2 positive. Then we have the mechanism proper, if you like. So I have my benzene ring. There it is. I'm going to show the delocalized ring like that. And I have my NO2 positive. Now again, you need to be careful with your curly arrows. You pick your curly arrows up from the ring, not the hexagon, because it's the pi bonded system which is being broken, not the sigma bonds between the carbon atoms. It's the pi bonded system. So please make sure you start your arrow from that ring of delocalized electrons. And those electrons are being drawn out from the ring towards the positive charge. So we get our intermediate. And our intermediate, we've broken the delocalization over one of the carbons. That NO2 group has joined on. So we need to show that break. So please notice that break is facing towards the carbon where we've got this nitro group added on. And we've got a positive charge inside the horseshoe. We call it a horseshoe shape. So be careful that you only break the delocalization over this carbon and that it's pointing in the right direction. It's a classic mistake that students make on this one. Well, we now need to reform the ring because that's going to be really unstable. So we're going to take the electrons from the bond between the carbon and the hydrogen, and we're going to use those to put back into the ring. Again, notice I'm picking the electrons up from the bond. And I get my nitrobenzene product with my NO2 group on it, and I've got my hydrogen ion that has come off and come loose. Last but not least, we reform the catalyst. So remember I said at the start that it was the sulfuric acid which was acting as the catalyst. So that extra hydrogen ion that we've just generated goes to reform the sulfuric acid, and it goes back to H2SO4. So controlling the temperature in these reactions is really important. Our conditions are that we heat under reflux of 55 degrees Celsius. If we allow the temperature to rise too much, for example above 60 degrees Celsius, it's possible that we'll get further substitutions onto the ring. So we could get dinitro or even trinitrobenzene as a product. So the next reaction we're going to look at is the bromination. That's adding a bromine atom to my ring. So the reagents are bromine, and that is bromine liquid. Please notice it is not aqueous bromine. That won't work. You're going to need something a bit stronger than that. Obviously, we know about benzene, but we also need a catalyst. And the catalyst we generally use is iron 3 bromide, FeBr3, as my catalyst. And again, the conditions are heat under reflux. Okay, so again, we've got the same 3 steps. first of all, we need to form our electrophile. So I'm going to take my iron 3 bromide, FeBr3. I'm going to add my bromine to that. Now my FeBr3 is what's called a halogen carrier, so it's good at actually picking up another bromine, so it becomes FeBr4 negative and leaving behind my electrophile, my Br positive. The mechanism, very similar to the one before. We have my benzene ring, my ring of delocalized electrons. We have my Br positive. Remember, curly arrows show movement of a pair of electrons. So the pair of electrons is coming from the ring to the bromine. It will show the movement of the direction of the electrons. This makes my intermediate. Again, I'm going to break the delocalization, but only over where I have my extra group. So in this case, I'm just going to bend it around like that. So my horseshoe is pointing at the carbon where I've got that break, and it's not over any other carbons. So I don't want any smiley faces, please, and make sure it's pointing in the right direction. The electrons in the bond between the carbon and the hydrogen are going to go back into the ring to reform that ring, and I get my bromobenzene product, and my hydrogen ions come loose over there somewhere. Reforming the catalyst, same as before, I have my FeBr4 negative. I'm going to add the hydrogen ion to that. So I'm going to make a secondary product, because remember, this is substitution. This is not addition. So I'm going to get an extra product. My extra product is hydrogen bromide. And I also get FeBr3 back. Now, there are two more reactions you need to know, alkylation and alkylation. And these are called the Friedel-Crafts reactions. They're named after the two scientists who developed them, Mr. Friedel and Mr. Kraft. So alkylation, so notice the spelling, ALKYL. Now this is adding an R group, an alkyl group. So an alkyl group is basically a carbon chain. Okay. Now the reagents for this are a halogenoalkane, usually a chloro, and my catalyst is AlCl3, aluminium chloride, aluminium 3 chloride. Again, that is a halogen carrier. And again, we're going to heat under reflux. The first step is to form the electrophile. So I'm going to take my aluminium chloride and I'm going to take my halogen, and I'm going to use chloromethane for this one, but you can use any halogenoalkane you like. And I'm going to remove, so that should be a 3, I'm going to remove this chlorine to make AlCl4 minus, and I'm going to get CH3 positive. Okay, this is a halogen carrier, so the aluminium chloride picks up that additional chlorine to become AlCl4 minus. Mechanism is again the same. I'm going to take my benzene ring. I'm going to take my CH3 positive. Arrow goes from the benzene ring, or the ring of delocalized electrons, to the carbon, which has this positive charge on it. So do make sure you're putting the arrow to the carbon where the positive charge. So wherever you've lost the chlorine, that's where you put your arrow to. And again, we get my intermediate. And again, it's got a positive charge. And I've got that CH3 group joined on now. And I've got that additional hydrogen. Electrons go back into the ring. And I get my methyl benzene, in this case, as my product. And my H positive. And again, I'm going to reform my catalyst. My hydrogen ion will react with my AlCl4 negative to regenerate the catalyst AlCl3 and to make my secondary product, which in this case is HCl. So the last of these is alkylation, a CYL, and this is adding this COR group on. So again, the reagents, very similar to before, I need a halogen carrier, Al Cl3, which is acting as my catalyst. And this time I'm going to use an acyl chloride, ACYL, because it's alkylation, acyl chloride. And surprise, surprise, it's heat under reflux again. So same reaction as before. I'm going to take my aluminium chloride, AlCl3, that's my halogen carrier, and I'm going to take my acyl chloride. In this case, I'll use my straightforward simple one, ethanol chloride, and my ethanol chloride is going to give up this chlorine, so I get AlCl4 minus, and I get my CH3 bonded to a C, double bond O, and a positive charge. You should be getting familiar with this mechanism by now. Hopefully you should be able to do this really on your own now. So I've got my carbon with my positive charge on it. Do remember that's where my electrons are going. They're going to positive charge. I get my intermediate cation, breaking that delocalization only over one of the carbons, making sure I've not got any silly smiley faces on this. Remember, there are no smiley faces in chemistry. And my H, and I go back into my ring, and we get our final product with our C, double bond O. So I've made a ketone functional group. And obviously also I've got my hydrogen ion. Let's come loose. Reforming the catalyst, same as before, hydrogen ion plus Al, Cl4 minus, goes back to Al, Cl3 and HCl as my secondary product. So that concludes this video, just looking at the reactions and mechanisms of benzene. As I said at the start, the mechanism of benzene is one of the most important you're going to come across in the upper sixth, and you need to learn it carefully, thinking about the movement of electrons, remembering to pick them up either from a bond or from a lone pair, but nowhere else. In the next video, we're going to be looking at the compound phenol in a lot more detail. So until then, take care, stay safe, bye.